Hello, welcome to another podcast starting out with quantum computing. Today we are covering niche things that you didn't know quantum computers could do. So quantum computers, everyone talks about them being the change of the future in terms of the computation landscape. But here we're going to be talking about what are some things that you didn't know that they can do. When you think quantum computer, you likely think, oh, it's this huge golden chandelier hanging from some squeaky clean laboratory. But is that always the case? Quantum computers can actually take form in many other applications in life, finance, gaming, the weather forecast, to name a few. So today we're going to take a look at some applications of quantum computers that you probably have not been completely familiar with. So the first one is quantum gaming. That's right, gaming, referring to video games. That industry is absolutely huge. You might have heard of Minecraft, Call of Duty, Wii Sports, games like this. And they all run on classical devices, classical computers, CPUs, central processing units, which are the hearts of computers. But we don't have to run them just on classical computers. We can also harness the speed of quantum computers. And quantum computation can be revolutionary for gaming. It can majorly decrease the loading times and processing times of popular games. For example, only 5 years ago, YouTuber Jabrils noted that through quantum simulation, we could heavily decrease the world generation time for Minecraft. Equally, Dr. James Wooten of IBM has created many quantum games already, such as Battleship and a quasi-Minecraft game. And games such as these can be fun to play, but can also be used to interest kids in the basics of quantum computing. And so only a couple of months ago, I stumbled across a LinkedIn post called Quandoom, which is the quantum version of a very popular game called Doom. It's a shooter-style game released in 1993, and colloquially, people in the computer science and technology community will say that any useful computational device should be able to run Doom. It's obviously a joke, but nevertheless, Quandoom has been created by a GitHub user, Lumorty, whose real name is... we're not sure, but regardless, he's shown that it can be run on a quantum computer that would have 70,000 qubits and would have to remain coherent, so functional, for 80 million gate operations. So how feasible is this? It is like asking a child currently to lift a car. But there's room for optimization here. 64,000 of those 70,000 qubits are used to render the display, meaning that the circuit to actually run the game only takes 6,000 qubits. So perhaps it'll be possible to reduce the amount of these display qubits, or to use a quantum classical hybrid approach, which is where we let the quantum computer do the inherently hard quantum stuff, and we let the classical computer do the rest. This would allow the quantum computer to handle this task properly. So a second instance of interesting quantum computing would be neuromorphic quantum computing. So traditional quantum computing makes use of the fundamental properties that we talk about. They're inherently quantum, such as superposition and entanglement. And neuromorphic quantum computing is an extension of this, where it essentially simulates and emulates the form of the brain. It's made up of artificial neurons and artificial synapses. And this approach can be really, really good. It can reduce the computational cost, the energy consumption. It can make solving things a lot faster. And quantum circuits that utilize this approach can be used to solve really hard physical problems really easily. So simulating molecules, for example, drug compounds, they generally are a hard problem. But with using neuromorphic quantum computing, it can solve it a lot more easily. And we can even employ this thing known as quantum circuit learning, which basically, over time, teaches itself and learns, much like machine learning, what is an optimal quantum circuit for this type of problem. So I have a problem, I'm going to check what type of circuit would be best, and if it doesn't run well, let me adapt that, let me change that, let me reduce the statistics, such as the total runtime and the total cost, in order to find the most optimal quantum circuit. Moving on to another niche application of quantum computing, quantum image processing and quantum movies. So quantum image processing, also known as QIMP with a Q, uses quantum computing to generate and work with quantum images. It's basically the process of taking a digital image and encoding it onto the language of quantum computers. And because quantum computers are inherently advantageous, for example, parallelism allows them to do multiple calculations at the same time, it's hoped that QIMP technologies will surpass the classical equivalent. This would completely change the way we store images, the way we send them, etc., etc. And in 2012, Iliassu and his colleagues proposed a way of producing movies on quantum computers. So by using this threefold system, where it's made up of something known as a quantum CD, a quantum player, and a movie reader, they are proposing that it will be possible to store all the frames of a movie in superposition. Then they'll perform operations on this device to allow the frames of the movie to play in sequence, much like any normal movie. And there would even be operations to facilitate playback and forward controls, much like your everyday TV remote. And of course, the viewer needs to be able to see the screen, to see the movie. So there would need to be a classical device to measure the frames of each from the quantum device in order to actually view the movie. And a key advantage of doing this is that it requires less frames to make the classical movie on a quantum computer to realize the same length movie. That is a little bit confusing, but essentially the quantum computer only needs less input frames and is able to, through quantum computation, fill in the gaps from one frame to the next by adding in filler frames, and on a usual classical rendering computer, when you're making a movie, you just have to simply put those frames in. So it could drastically reduce the cost required to produce movies. Most interestingly, a technique that allows for storing pixels of an image on a quantum computer is known as FRQI, Flexible Representation for Quantum Images. So by capturing the color and corresponding positions of every pixel, we integrate this information into a quantum state and form a quantum picture. And all frames of a quantum movie are going to be FQRI quantum states. And although right now this technology is in infancy stage, it could serve as a foundation for the future of movie production. So last on our list, but not least, is quantum Sudoku. So Sudoku, I'm sure, listener, you're quite familiar with it. It's a number puzzle game, but you might not have known that it originated in Switzerland, then traveled to Japan via America. So the puzzle is based off an ancient Chinese concept known as magic squares, which involves filling a square in with all the numbers from 1 to 9, such that each row, column, and diagonal adds up to the same number. That's magic squares. Similarly, in Sudoku, each row and column and box must contain the numbers 1 to 9 only once. And so the Swiss mathematician Leonhard Euler, put forward this idea in the 1780s. However, the problem of solving an arbitrary Sudoku puzzle remains non-trivial. It's always difficult. And this type of problem is known as a constraint satisfaction problem, which basically means that either it's just too complex because it takes too many steps to solve, or because there's a discrepancy. Sometimes the steps have to be applied sequentially, or other times they can be applied in parallel to give the same solution. So, although a quantum solution for infinitely large Sudoku, let's say of size arbitrary n, has not yet been reached, this recent research paper by Anker et al. Have shown that a quantum circuit can solve a 4x4 Sudoku puzzle. And it does this in a very interesting way. It assigns each possible cell to a qubit and then uses superposition to represent all the cells at once. Then the algorithm progresses and it starts to delete the incorrect solutions from the superposition, leaving only the correct answers in each cell. And although very impressive, there are also some drawbacks to this. So the chances of the algorithm reaching the correct solution, it's not 100%. And the algorithm is quite heavy on qubits. And it also requires a bit of classical help. So there'll be a classical computer, classical device on the side. And what it's doing is it's cluing the quantum computer in on which cell it's likely to delete next. So this will increase the overall computational cost. So to conclude, quantum computing is so diverse, and it's being applied to almost every field you could think of that involves a computer and that will benefit from enhanced technology. And yes, it is still very immature in certain sectors. The promise of increased speed and reduced cost is what drives funding and research today. Quantum computers, they have the ability to completely change the way that we compute. It's a completely different way of computing. It's not even made up of the same fundamental blocks. And quantum computers have the benefit and promise to reduce the amount of resources required to tackle problems. So even in very niche areas, such as quantum gaming or quantum movies or quantum Sudoku, we can still find quantum advantage after all. Thank you very much, and hopefully I will see you on next week's podcast.